Hello. So this is a continuation of the last lecture I had taken, titled Convolution in Matlab. Okay. So in this, what we're going to do is we're going to use a different method. The method is very simple. I just explain it to you. Okay. So we want to convolute, this signal x of n with this signal h of n. Now, in this method, we'll create a table like this. Okay. The table, how to create the table, I'll tell you. The table is created in this fashion. We'll do x of n multiplied by the first value of h of n. Okay. And this x of n, we'll write it as a column and multiply it with 1. So you'll get 1 into, since all of these will be multiplied into 1, you'll get the same values 1, 1, 2 and 3. Okay. Further on, what we'll do is we'll multiply the same row with the second value of h of n, giving us 1 in times 2, 2, 1 times 2, 2, 2 times 2, 4 and 3 times 2, 6. Now we see that that's it. H of n ends there. So for simplicity's sake, for right now to just show how the table works, what I've done is I've put zeros here so that we end up with a square matrix. Okay, 4 rows and 4 columns. Okay, once that is done, so we have created our table. Okay, this table will help us find out the convolution matrix. So we'll mark these tables in these kind of diagonals. So this will be like one section, this is the other section, this is the third section, fourth and fifth, so on. Okay. In each of these sections, we'll be adding it across the diagonal. Okay. Now these are not the normal diagonals that you talk about a matrix, this one, but these are in this fashion. Okay. Now this is the important part. For the first element of the convolution, if you remember the answer that we had got in the last example, this is the same example we're continuing from last time. We had gotten the answers 1, 3, 4, 7 and 6. You can verify from the last video. Here, if you add these numbers across the lines that I have taken, we will get the terms of our convolution. Like for example, this across the first diagonal we have 1, which is the first term here. Across the second diagonal we have 1 plus 2, which gives 3, which is the second term. The third diagonal gives us 2 plus 2, 4, which is the third term, and so on. Okay. So if we just keep adding numbers across the diagonals of this table, then we will find our convolution matrix. So this is also a way of finding convolution. It is one of the shortcuts, or one of the easier ways of finding it. And as we go to implement this in Matlab, we will see that this is much simpler than the last method that I had discussed. Okay, so that's it. I will just go to Matlab and we can see how this can be done. Okay, so coming back to our favorite software, Matlab, we'll see how we can establish the logic that we just studied into this. So to test this file, I'm using the same input, same data signal and same system as we had considered in the last example. The only change in this test program I'm doing is I'm changing the function from convolution 1 to convolution 2. Okay, just changing the function from convolution 1 to convolution 2. So this is the advantage of using functions, is that even if you change a small part of the code, you don't have to change a lot of things. Now this entire program is the same as the last program. I'll just change the way convolution is implemented. I've also kept the input and output format same, so that nothing else needs to be changed. So let us now see how the convolution program is written. I open the convolution 2 program. See, this is a much shorter code than before. I'm using none of the earlier functions that we had used. All the functions used in this file are defined in Matlab. We don't need to create anything extra. Okay, so this part of the code should be pretty much clear to you if you have seen the last video. What I'm doing is basically just creating the time axis for the convolution. Okay, now the task we had in hand was, like, say, our matrices are x was 1 1 what's that? Sorry, 1 1 2 3, right? Okay, just wait a second. Okay, let's say our x was 1 1 2 3 and our h and n was h was 1 and 2. Okay, so the matrix, say, let's say the matrix that we want to create is called y, and we know that it will look something like this: 1 1 2 3 and 2 2 4 6. Okay, the first column comes because of this thing into 1, the second column comes because of the same thing into 2. Okay, now how do you create this matrix? So the code I've written to create this matrix is this code. Okay, I largely depend on vectored notations or the subscript notations that I was talking about, and the reason I stick to it is because it's very interesting, and it makes the code simpler. So to get the first column, what we can do is we can multiply this entire matrix with 1. Now this entire matrix is a row matrix, okay, and you're multiplying it with 1, which is just a single constant. See, when we consider of the entire h, we know h is a 1 cross 2 matrix and x is a 1 cross 4 matrix. But now I'm not interested in multiplication of x and h. I'm interested in multiplication of x, the entire row matrix, into h1, right? So this multiplication is a normal multiplication. It is like multiplying a row matrix, or multiplying, for matter, any matrix with a scalar value. Okay, so the dimensions of it will not change. Okay, so what we have is 1 1 2 3 into 1 will give you 1 1 2 3. Now this 1 1 2 3, I want to save it in y as a column matrix. Okay, see to it. X is a row matrix, multiplying with h with scalar will just give you again the same row matrix, but I want to save it in y as a column. Okay, so how am I saving it in y? I'm saving it y as different rows and the first column. Okay, so this is like your row 1, row 2, row 3, row 4, and this is your first column. Okay, so the way to save this is you write the simple instruction. I would write, okay, let me change the color. I will write y, okay, y colon comma 1 equals x into h1. Okay, there should be an asterisk in between. See, x into h1 is simple, 1 1 2 3 into 1. Okay, and I save this as y colon comma 1. See, we know that when you write in subscript indices, the first value shows rows, okay, and the second value here shows columns. Now we are sure that the data that will come here we have to store in first column. That is not changing, so we can keep it as a constant 1, right? And we know that the rows that will come will depend, we don't know what the rows are, right? But what we want is we want it to be stored as rows. So I put a colon here. The colon stands in this case for all. So I will read it as this: y of all rows comma first column is equal to x into h1. Okay, try to make this idea very clear because it is very useful in Matlab. So y of all rows, because I have written a colon, comma first column is equal to x into h1. Okay, so now you will, for the first column, for the first column of y you will do that. For the second column, what we will do? We will do y colon 2, right? Because y of all rows second column is equal to simply x into h2, right? Now how many such columns will we get? Okay, the number of columns we will get will depend on the length of h. Okay, will depend on the length of h. Now what is the length of h? The length of h is simply the length of m. So we will run, so instead of writing y colon 1, y colon 2 for every such line, we will put it in a simple loop so that the program becomes generalized also. Okay, so you will put for I is equal to 1 to length of m. In this case, say m will be m will be your -1 and 0, and length of m will be 2. So y is equal to, for I is equal to 1 to 2, you'll have y colon I is equal to x into h of I. Okay, so this piece of code, these two lines here, it gives us our table. Okay, so once our table is defined, if you remember, once our table is defined, we need to add the diagonal elements like this. Okay, we need to add these diagonal elements. So what I'll do is, again, let's take a simple copy. Let's take an example. Okay, just to explain this better, let us actually see this slide here. So what I've done is, this is the table that we'll create, right? We have done this part. I'll extend this table further on, to add these zeros, here. Okay, the reason will be very clear right now. So the first element will come by this diagonal. Okay, so y of 1 1, the first element here, is simply y of 1 comma 1. Okay, first row, first column. On the same lines, y of 2, that is the convolution, the second element in the convolution, is y of 1 comma 2, this element, plus y of 2 comma 1, this element. y3, the third element in the convolution, is y of 1 comma 3. See, in our original matrix, it is only of this size, so we don't have these zeros here. But for the sake of programming, we'll just implement these zeros here and see what will happen. Okay, so y of 1 comma 3, this term, okay, the diagonal that we are considering is this diagonal. Okay, y of 1 comma 3, this term, y of 2 comma 2, and y of 3 comma 1, and so on. So if you go on by this pattern, you can see the pattern that is forming is here. We are, for each term, let's say y of 4, we'll start y1, and the row number will keep increasing. Okay, 1 2 3 4 will increase till this value n, and the column number will start decreasing, 4 3 2 and 1. Okay, so to implement this, if you see the sum of these terms, okay, 1 plus 4 is 5, 2 plus 3 is 5, 3 plus 2 is 5, 4 plus 1 is 5. We can have one loop. Okay, let's say you have a for loop. In that I will vary from, like, say for the fourth term, when you're talking, you'll vary I from 1 to 4, and you'll simply have y of something, whatever term that you're seeing for. Y of 4 is, okay, y of 4 is y of 4 plus y of I. Okay, this is the row. For 4 values, 1 2 3 4, 1 2 3 4, you'll have your rows, comma 4 minus I, comma 5 minus I. What does that do? When you put it 5 minus 1, see, when I is 1, you'll get 1 comma 5 minus 1, which is 4, which is your first term, right? When I is 2, you'll have 2 comma 5 minus 2, which is 3, right? Second term, third term, fourth term. So writing it in this form has generalized by this equation, right? Is that clear now? The reason we are writing this equation is writing it in this form is generalized by this equation. The only problem I'm having right now is for y4, which is this term. These two things are non-existent. Okay, these two zeros are not existent. So the first and second terms, y of 1 comma 4 and y of 2 comma 3, these are not existent for me. Okay, they do not exist. So what I can do is, in this while loop, I can write some if condition that when you are searching for y of I, which is not existent, do not add it into the sum. Okay, now let's go back to the program. Okay, let's go back to the program and we'll check it out there. Okay. Now in our program, see, till this part it was clear that we have managed to make our table. Okay, here we will define the length of our convolution matrix. Okay, we are defining yy. Okay, the convolution, this answer that will show in convolution, will fill it up with zeros. The reason for doing that, is here I'll tell you why. Okay, so let's look at this statement later on. Now, how many times will we run the main for loop? Okay, the main for loop will run the number of times for each term in the convolution. We'll have to run it once. Now, how many terms are there in the convolution? There are nn. So length of nn. So when n is equal to, your capital N is equal to 1 to length of nn, that is the number of times you will run the loop. Okay, so when n is equal to 1, you will get a y of 1, y of 2, y of 3, and so on. Now, this loop is to be run for every y. Okay, so for y of 1, you will run this loop. For y of 2, you will run this loop, and so on. Okay, so for y of 1, your n will become 1, right? So you will run this loop 1. You will have j. See, instead of having I and n minus 1, n plus 1 minus 1, what I'm doing is I'm having I comma j, and j I'm defining here. Okay, j is your n plus 1 minus I. This equation I discussed before, right? So the first, you will have y of 1 equals y of 1 plus whatever is your table element. Okay, so if you are searching for y of 2, you'll have y of 2 plus y of 2, and the number of table elements. This if equation here, this if statement here, it is used to to remove the extra zeros that we had added, right? This formula here, it assumes that the table is big enough and there are extra values there. Now this if loop, it allows your program to enter into this only for those values in the table that are existent. Okay, only for those values it will, this if loop will follow. Why? See, we have kept if I is less than equal to length of n, okay, which will show your row, and if j is equal to less than m, which is your column. So your table is only defined for n values, n rows and n columns. Okay, apart from this, anything you have added is not part of your actual system, right? These are your zeros that you have added. So we have put this if line that if I and j are belonging to this group, only then will you sum them, else you will not sum them, right? I hope that my explanation was good enough. In case you don't understand, you can point out which part you don't understand, and we can study it together. So once that is done, our system is ready. Okay, now the reason I told you that we had used this line is, see here what we are doing is y of n is equal to y of n plus something. Now initially, so let's say you are doing y of 2, y of 2 equals y of 2 plus something. Now if y of 2 is not existent, then this will give a Matlab error, right? So for the first time you run y of 2, what we can do is we can fill y of 2 with zeros. Okay, you can initially start a y matrix in which there are all zeros. Okay, and slowly you can add things together to get your answer 1 1 1 3 4 7 6. Right? So initially they are zeros. To make this initial matrix, we are using this line here. Okay, so you are initially populating the y, and slowly your program will change the value of y to get the convolution answer. Okay. So that's it. We'll just run the system and check it out. So in our test file, I've just used as fiction the function convolution2, which we have defined here. Okay, this is our convolution2 file. And just one thing, before plotting it, I will rectify the mistake I had made earlier. We will write the titles also. Okay, so this is your title x of n. This is title h of n, and your last one is y of n. Okay, let's save this file and run it. So once you run it, you will get a convolution here. See, 13476 at times minus 1012. Okay, and this is your plot. x of n, h of n, and y of n. Okay. Thank you for watching this video. Uh, this is one easy way of implementing convolution. What I'll do is in the next video I will show you how to do convolution with the traditional formula that we have. Okay. So thank you.